Good afternoon, everyone. Let's continue with today's program. Now, I would like to introduce our second presenter. Our next speaker is Ms. Kulas Talabiden from Department of Robotics and Mechatronics, Nazarbayev University, Kazakhstan. Hello, Ms. Kulas.
Hello,
Yes.
can you hear me?
Yes, I hear. Let me briefly introduce her. Miss Class received a bachelor degree with honor in technological machinery and equipment from Kazakh Agro-Technical University in Astana, Kazakhstan in 2020. She then completed her master degree in robotics at Nazarbayev University. Since 2022, she has been research assistant at the Power Conversion and Motion Control Laboratory, focusing on motion control system. Currently, she pursuing a PhD in robotics engineering. Her research interests include electric drive system, control system optimization, motor drive control, and automatic system control. Today, Ms. Class will present her work title, Neural Network-Based Adaptive Input Shaping for Payload Oscillation Suppression of Tower Clamps. This study proposed an adaptive control strategy that combines position control with input shaping to enhance the accuracy and flexibility of a 5DOF tower clamp system. The results evaluated two methods, neural network-based input shaping and gain scheduling via lookup table, and compare them against traditional open loop control approach. Laboratory experiment show that the proposed method can reduce payload oscillation by up to 78% compared to traditional control, and by 53.8% compared to open loop input shaping, while maintaining high endpoint precision under very operating conditions. This result highlights the effectiveness of adaptive input shaping in achieving prices and stable clamp operation. Let's welcome Ms. Class. Are you ready for your presentation?
Okay, let me share my screen.
Please share your screen and begin your presentation.
Can you see my screen?
Yes, I see. So good.
Okay, so the topic of my research is neural network-based adaptive input shaping for payload oscillation suppression of tower crane system. My name is Kulyas Talapetyan. And here's a brief outline of today's presentation. So first we'll begin with the context of the tower crane system and the key challenges that they have. Then we'll define the problem statement, discuss the motivation behind the exploration of model-free adaptive control methods, also the proposed method, hybrid control approach for tower cranes. Then we'll see the implementation for the system, experimental results, provide the discussion, and give the brief conclusion. So load handling has progressed from human labor to complex system with precise and dependable operation with the help of developments in automation. As we know, cranes are mechanical structures used for carrying and transporting heavy items or even some hazardous goods. They require the secure transportation of large and dangerous objects in many different areas. The main types you can see in the figure 1 with a gantry crane, tower crane, boom crane, and on the down part you can see the absence of the appropriate control system and its damage to them. So In the next slide, you can see the problem statement. So one of the primary technical challenges for the tower crane operation is the persistence of the undesired payload oscillations. Oscillation can occur due to the pendulum-like behavior that you can see on figure 2. And it can also be affected from the wind disturbances, also from the combined motion of the trolley and tower rotation, which we'll also see from our experiment. So this swinging possesses severe consequences, such as reducing overall system efficiency, increasing the time to the completion of operation, and increase the risk for the collision of the object and damage to the populated areas. So thus, the minimizing oscillation while achieving the precise payload positioning is critical for the improvement of the crane system performance. Sorry. Here we can see the mathematical model for the tower crane with the consideration of the dissipation function. The model was derived using Lagrangian approach, so we can see the tower crane present a highly nonlinear dynamics which require an advanced control strategy to ensure optimal performance. Traditional model-based methods have long been used to maintain accuracy and stability by relying on the precise mathematical model for the system. However, due to the uncertainties that the system often fails in practical application and on model dynamics and existence of the external disturbances, the methods can fail. However, when we see the non-model based approaches such as machine learning, they can offer significant advantages over the traditional control methods. So these methods can adapt to real-time data and adjust control strategies dynamically, providing the robust performance in even under unpredictable conditions. So here in practical operations, purely open loop control and closed loop control, they are combined because open loop control can suppress the oscillations effectively. However, closed loop control can provide the precise positioning of the trolley and the jeep. That is why the current research, they are focusing on the hybrid input shaper using fuzzy logic controller and also the traditional one PID controller, which is easy to implement. So let us start from the open loop control that we implement to our system. So input shaping is an open loop control specifically designed to mitigate resonant vibration. And the basic idea is to modify the input command that you can see on figure 5 using a sequence of impulses precisely timed and scaled so that induced oscillation from each impulse destructively interfere, canceling each other. So the basic one is a zero vibration input shaping that made with the amplitude and time delay, and more robust version of it is zero vibration derivative, which we implemented in our case, and it can provide some robustness for the model uncertainties. And the shape command you can see on the following figure. However, the effectiveness of the input shaper depends on the accurate knowledge of crane's nature of frequency, which changes with the hoisting length. So hoisting is a process when we put our payload to the different height. And in order to avoid to increase the robustness of the input shaper, in this research we compare two adaptive techniques. One of them is a neural network, and the process how to design the neural network is shown on the flow chart on figure 6. From the left side, you can see how we can design the neural network, and it also was compared with the gain scheduling method, also adaptive technique that uses lookup table, and the process of this also you can see on the right side. But before adaptive technique will be implemented, first we conducted the experiment in which we collected for each cable length from 0.05 meters until 0.8, which is the parameters of our tower crane. We calculated according to the previous equation our amplitude and time delay. So determined natural frequency, damping ratio calculated, and then we found the neural network, designed our neural network, and lookup table. Here you can see our neural network framework, in which you can see the input for our feed-forward neural network was cable length. It went through the hidden layers with the 6 neurons. And then in the output, we were getting the parameters of 3 amplitude and 2 time delay for the 0 vibration derivative input shaper. Our neural network was divided to the training and validation set with 85 and 15% division of the data set, and overall accuracy can be received of 99%. And on the right side, you can see the mean square error for the neural network of input shaper parameters. So you can see that it quite well can find the parameters of the shaper. Then here is our experimental setup. It is in our laboratory, power conversion and motion control in the Nazarbayev University. So our experimental test bed is a 5 degree of freedom tower crane equipped with a 5 resolutional optical encoders achieving 40,096 pulses per rotation and the swing detection until 0.015 radians. The control system is built around using RTDC board FPGA and embedded with FPGA, and this setup is equipped with 3 BLDC motors and with emergency stop switches, ensuring the operator safety during the real-time testing. So firstly, we compared with the traditional open loop control that is existing for the literature. So some of the literature already focused on the adaptive control, but providing with the input shaper. We compared 3 methods, which is average travel length, which is also one of the methods in which we can design input shaper based on the average length. So for example, on the down part here, you can see that we made our experiment from 0.1 until 0.5 cable length. So we designed our input shaper on 0.3 to provide the also the robustness according to the literature. The next method was lookup table and neural network. So this input for the system was a trolley motion, tower rotation, and hoisting. Okay, so here we can see that from the following figure that open loop cannot provide the precise positioning for the Jeep, while we gave the in radians it is 0.79 radians, and for the trolley we provided 0.7 input. So not trolley and Jeep couldn't achieve the desired position. However, we can see that swings were suppressed effectively using all 3 methods. So here we can see that we compared this with the 3 main cases in which crane operates. The first one is the trolley position, in which we compared with the trolley and the hoisting motion. 3 methods shows a good performance. However, the better one we can see that neural network. In the next case, we compared with the tower rotation only, in which we moved tower to the 45 degrees and then compared the oscillation in X and Y angles. And the next one is the case 3, in which we can see the simultaneous trolley displacement, Jeep rotation, and payload hosting, in which we can see the lowest swings is shown with a neural network on the down part on the right side. So as we saw that open loop control cannot provide the precise positioning, in this research we focused on the hybrid control, in which we combine the PID control for the closed loop position control, and for open loop we use the input shaper and provide the adaptive mechanism. On the right side you can see the tuning parameters. So for each case we were needed to tune for each method. So here you can see the experimental results of hybrid control. From the case 1, we can see that now our trolley can follow the reference and provide the performance correspondingly, and the low oscillation close to zero can be seen for the neural network in each case. Especially we can see that for the complex motion, neural network provides almost zero oscillation during 10 seconds, okay, which can be seen on the case number 3. Okay, and here I wanted to show the experimental results with the no control, in which we can see that we tried to rotate it for the 45 degrees, however it couldn't provide, and the oscillation with the no control, it can be seen quite high, but with the providing with a neural network, the almost zero oscillation in both X and Y angle can be seen on the right video. Okay, so in order to provide the comparison between open loop and hybrid control, error evaluation metrics using means absolute errors was conducted. So here we can see very low error can be seen for the case number 3 using PID plus adaptive input shaping control using neural network. In this research, we compared 3 adaptive techniques that combined with closed loop control under different crane motions. Overall, it can be concluded that all 3 methods can provide good results. From the right side, you can see that for the last case, neural network and ATL approach, so the least oscillations in terms of y-axis provides neural network, and in terms of x-axis we can see that ATL can show less oscillations. In addition to this, in order to provide to show which methods can be used for and optimal, we check the computational time. And overall, it can be concluded that for the small motion, simple motion like tower rotation, we can use the lookup table and ATL approach. However, for the high precision operation and simultaneous tower rotation trolley displacement, neural network with PID provides better response despite of the high computational time. So here again, the conclusion of the presentation. Overall, tower crane remains challenging to because it's underactuated system with non-linear dynamics. Open loop can provide good sway reduction, however, with a precise absence of the precise positioning, and the hybrid control can be implemented with a easy easy to implement PID control using plus adaptive input shaping. Experiment has been conducted for this research, and overall we can see that neural network can be used for the high precision task, and with a simpler motion, ATL and lookup table can be used. So here's a reference list of the this presentation, and thank you for your attention. And if you have any questions, you can ask. Okay, so can you see still my screen?
Yeah, I see.
Okay.
Thank you very much, Ms. Kulas, for presentation. Anyone can raise your hand or type question. Okay, invite Châu Trung Tính.
Good morning, everyone. Good morning, class. I am very happy to hear your presentation, but I have one question. And I understand when we apply the neural network to the control system, the network will approximate the system character. However, it's always have the approximation error. And in your design, what's the strategy did you use to minimize the impact of the approximation error on your system to improve the performance and stability? Thank you.
Okay, sorry, can I clarify the question? Are you asking about the architecture of the neural network? What was the process of that?
Yeah, sure.
Okay, so here while we were training the neural network, first we were dividing our data set with the training and validation, and then checking with the mean square error. We compared with the real value that we saw from the data set. And here from the plot, you can see that it almost can capture to the exact parameters for the real shaper.
Yes, thank you, Kola. Thank you.
Anyone with question? I had a question. How many sensor you require for power adaptive stepping system? How many sensor?
Okay, so here we can see 5 optical encoders that was used for this case. And the parameters of that, for the measurement system.
How does the sensor noise affect the stability and reliability of adaptive stepping?
So
Sensor noise.
I'm not sure. Like here we saw that this very quite low values for the affecting of the system. That is why it is almost precise. So until 0.001 precision.
Thank you. The sensitive is the neural network to measurement noise or sensor error is affect to system. Sensitive. From sensor. Okay. The sensor error. Sensor error.
Okay.
Because I think this system so many sensor, and if one sensor problem, not how affect to system.
Okay, but I will check the question. Okay. Possible. The system errors was quite low, as I remember from the experiment, what I saw, but currently I cannot answer to this question precisely.
Yes. You the input selected for neural network model. How you choose the input?
Input to the system was cable length because in this research we were focusing on the hoisting process, which is quite spread to the industrial applications, construction applications. Okay, so here we can see that cable length was input to the system from the data set that we collected. So from each length, we collected the data with the corresponding natural frequency and damping ratio.
1 second for testing.
Okay.
Okay, thank you for your explanation. Anyone else with question?
I have one question. Like, do your neural network use the generalization to handle the overfitting? Because when we're training, something happen, like it will be the overfitting. And do you use something to change this?
I use the early stoppage for the epochs to prevent the overfitting. This on my codes.
Yeah. Yeah. Okay. Thank you.
Okay, I see maybe have the question from Mr. Phạm Thế Tiệp. Okay, please.
Okay, thank you so much for your presentation. My name is Dev. I'm from Hanoi University of Science and Technology. And regarding to your topic, as I know, we have to do 3 steps. The first step is develop the model. The second is finding the path planning. And the finally is design a controller. So now in your topic, you are focusing on the controller design. So I want to ask about the previous step. How can you develop the model and how can you find the path planning to control?
Okay, so in the beginning, I told that due to the model complexity in this research, we were focusing on the model free-based control. That is why for the we used PID that we tuned, and also we used input shaper that doesn't require any model. Just requires the parameters of the shaper, which we made according to the experiment, where we collected the natural frequency and damping ratio, shaper parameters for the open loop, and that's it.
But I want to ask about the reference. The reference path. The reference is optimized. Should you optimize the reference path before you design the controller?
I checked from the literature and found the common references that is used for the tower cranes. So I used that.
Okay, so as I know, if the path is optimized, so the controller is very easy and the controller could be much easier to design when the path is optimized, as I know. Okay, thank you so much for your answer.
Thank you for questions.
Yeah, thank you, Mr. Kulas, for presentation.
Okay.
Okay. On behalf of the organizing team, thank you. Thank you to Mr. Yusuf, Ms. Kulas, and all participants.
Okay, thank you very much, Dr. Wang and everybody, and including the speaker, and the audience for very nice webinars and sharing the research experience and discussion. Okay, thank you very much again. Okay, so and have a weekend, good weekend.
Thank you a lot, Professor Tao. Thank you for this opportunity.
Okay,
thank you a lot.
so see you. Bye bye.